So here's a conceptual animation of what we think we can do with this. We think we can assemble large space structures that link together in a non-contacting way with the magnets and superconductors. Now either we can drive these modules in with whatever your favorite scheme is, EMFF or thrusters or whatnot, and then you field cool superconducting elements establishing an equilibrium. Or you field cool the superconducting parts of the interface before you do any of this, and the components will all seek each other passively. They would fall into each other's potential wells, and the entire system can be assembled without any active control. So we have some questions that we need to answer about these interfaces. I've been talking about this invisible spring and invisible damper, so what are the mechanical properties of this interface? And what can we do to design these interfaces? What are the performance parameters? How do we change them? And once we have an interface, are there any ways that we can manipulate it? And again, I'm not to poo-poo active control here. We would like to be able to actively control things, but passive stability is nice in the event of control failures. So here's a physical model, or a mathematical model that we're using to describe the physical system. This was proposed almost a decade ago by Korjak, who worked on superconducting physics systems, and developed this model to reflect the flux distribution that's established within the superconductor. When you field cool the superconductor, so this side of the diagram here is all superconductor material. When you field cool it with a magnet in place, two images form. One of them is fixed in the superconductor, and it's a reflection of the magnet with the same dipole moment. And the other one reflects, literally, the current state of the magnet. So as the magnet moves around, this mobile image moves with it. Now you can see here that there's sort of a parallel with active control, even though this is all happening purely because the superconductor is a superconductor. When the permanent magnet moves, this mobile image moves with it, and since its dipole axis is approximately opposite, it's sort of repelling things. So if you imagine the magnet coming into the superconductor, this repulsive image moves towards it and pushes it away. If the magnet moves away from the superconductor, the repulsive image moves back, and the magnet is attracted to that frozen image. So it's almost like there's active control happening here, but you get it for free in the superconductor. And we're using a dipole model here because dipole fields have this analytical expression, and it's very easy computationally to deal with. When you're far away from magnetic field sources, dipoles are pretty good approximations. So we're using that right now to get our numerical results. We're also getting experimental results. We've got a test bed in our laboratory that's based on the magnet on a very long pendulum, and we flux pin it to a superconductor on a translation stage. So we can vary the initial field cooling separation between the magnet and superconductor to get an idea of what sorts of these, the stiffness, how it changes with the field cooling separation. After we establish this flux pinning, we use a coil driven by a computer to just excite the pendulum modes, and we track the system with the motion capture camera at high frequency. And as we do this, we excite all the different modes of the pendulum. One of the reasons to go to a pendulum here was to try to take gravity out of the equation and make a sort of space-like system. Not quite, we're still on the ground, but in the future we hope to extend this to a test bed for flux-pinned interfaces. But as we step the translation stage back and try different field cooling separations, we use the motion capture data to get a spectrum of the response out. And we track the shift in these frequencies as we change the field cooling separation, and figure out how the stiffness changes as the magnet and superconductor are pinned close together or further apart. So here's some data from this. The data points are a 100-gram magnet, which, the bigger magnet is, the magnet mass scales roughly with the magnetic field of the magnet. And then the dotted lines here are from the frozen image model that I discussed earlier. There's a certain range over which flux pinning works. I said at the beginning that a sufficiently strong magnetic field can be flux pinned to a superconductor. Below that field, you only get Meissner repulsion. So there's a certain separation distance that you must be within in order for flux pinning to link modules together. However, within that distance, and that's about here, you can see these data points are flatlining. This is stiffness in physical units of newtons per meter, and this is separation distance in centimeters at the time of field cooling. But once you get flux pinning, it goes up exponentially as the magnet and superconductor step closer together. So here we have stiffnesses going up to 1 to 5-ish newtons per meter in this 6 to 10 centimeter range. But as the modules get closer and closer together, you can get exponentially higher stiffnesses. We're talking about hundreds of newtons per meter binding modules together in a non-contacting way. You similarly get rotational stiffnesses, but we see these as slightly less important than the translational ones because you can construct rotational stiffness out of distributed translational stiffnesses. And here's a plot that looks at a particular metric we're using to characterize these interfaces. This is again stiffness of the interface in newtons per meter, and I'm plotting it against the flux density that we measure at the surface of the superconductor. So essentially it's asking how much stiffness do you get if you can project some amount of flux from the magnet to the superconductor. And this is a power law relationship that we've confirmed with the image model, and we're measuring here experimentally. The important takeaway message from this is that if you have a magnet closer to the superconductor, you get more stiffness, but also if you have a bigger magnet, you get more stiffness. So the blue points here are a magnet that's smaller than the magnet I previously described, but they still fall along this line. So we see this flux density at the superconductor as an important metric to characterize these interfaces. Now, are there any ways that we can design this? How can we change the properties of the interface to give it certain behaviors? How can we change those properties on the fly? One way that we've been looking at is to use various metals to try to influence the flux distribution in the superconductor. So for instance, we have this pendulum with the magnet, and we have a superconductor in a liquid nitrogen tank. We can put some iron behind the superconductor before we cool it. And the iron will sort of attract the magnetic flux lines and shift the flux distribution in there. And it turns out that when we do that, we get a sort of a trade-off in stiffness. The translational stiffness drops a little bit, the rotational stiffness is boosted a little bit, and we're still characterizing this. But the gist here is that with some distribution of ferromagnetic material or material that has a magnetic response, you can alter the stiffness of this interaction, and you can get an actuator that you can get an interface that has certain desirable properties. Now, in the interest of actuation, I should mention that the magnet is still going to respond to electromagnetic forces. So if you pin together some modules, you can then adjust their positions by having an electromagnet that pushes on the magnet. So here is our superconductor, here's our magnet, and this little ring is simply an electromagnet coil. And as we change the current in the coil, we can get this magnet to bounce around. So you can establish flux pinning between modules to bind them together in this non-contacting way, and then you can sort of bend the modules around next to one another with magnetic actuation. This is one way to get reconfiguration of modular spacecraft systems.